So we're recording. Did it ask you? No, it's not asking anything.
No, I will just camera reset. Okay, it's good.
So welcome everyone to the first talk of the Working Group 2 meeting, which is by Alessio, and he will talk about all the interesting things he did during his PhD. At least a subset of it, because probably you can speak for 2 hours otherwise.
Yeah, it's about reconstructing SMT proof.
Yes.
Oh, okay, again. Yes. It works?
Stand there.
I stand there. I press.
Like again.
Ah, yes.
You have a camera that is following, that should be following you.
Yeah, look at the screen.
Look
over
at the
there.
screen.
It works.
The camera is
I can see it.
following.
Okay.
Okay, the test pass. It's just a test. It's not a proof. So I'm here for talking about reconstruction of SMT proof in Lambdapi. So it's related about the correctness of SMT solver, because SMT solver are large base of code of C++ most of the time. So it's like there's like many bugs that can be inside this large code base. And every years during the SMT competition, solvers have different output for the result. So can we really trust their result? So the natural idea that you can have is like you try to certify the SMT solver. So you try to git clone CVC5, for example, and try to prove that the code of CVC5 is correct, which is maybe maybe millions of lines of C++. So I'm not so sure you want to take this approach. And if you do this kind of things, you might try to simplify the code, which like will sacrifice the performance of CVC5, because sometimes just proving that a C++ code is correct is like very difficult because of recursion or these kind of things. So, and also like if you certify your software, then you become like kind of frozen. So if you add like a new feature, then you need to reprove everything that's like is still correct, like your invariant is correct and all these kind of things. So it's like not the best approach. So one of the approach that we are doing is like proof logging, which is like the SMT solver will give you a trace, like a proof trace, okay? And then you will like try to check that this proof is correct. And you can do this with an independent software. It doesn't need to be embedded in your SMT solver. And the good thing is like checking should be quicker than solving, okay? Because it's just a proof trace. So one of the solutions that Alessio created is the ALT format. So it's a proof trace format for SMT solver. It's based on the SMT lib. And it looked like, a judgment look like this. So you will have steps in your proof as like a natural deduction proof, okay? But all the steps as an index, then you have a context, closed because you're doing such solving, and then rules like the elimination of the conjunction or other logical rules, premise that are just reference to the previous index, and some argument that you can pass to some rules. It will create you, the proof will have the shape of an acyclic graph because it looks like a natural deduction proof, so it looks like a tree. And in the set of rules, you have some rule that will be specific for the theory of the SMT solver. But I will give you like a kind of overview of all the rules. So let's take this input problem that will be our first guiding example. So that's, I think all of you are familiar with SMT, but I will just like be short on this. This is the most smaller example I could find. So here you declare a sort U that has an arity 0. For the others, like a type logician call this a sort. So you declare a function here, like so it's a constant A and B, then a predicate P that take element of type U and return you a Boolean. And then you assert 3 things, and your last assert will be your goal. Okay, so you assert here that you have P of A, you know that you have A equal B, and then you want to prove that P of B, you have P of B. You do the negation because you do the it's how SMT works, like the negation of this, with a negation, then you prove that something is valid because you prove a satisfiability. So here it's like you're doing a proof of unsatisfiability. And that's ality in the concrete syntax. So it looks like this. So the three assumed here are like the steps that represent the assert. Okay, so there is no rule here because it's like the rule can be like admit. And then each step, so this is the eye of the ality judgment I just showed you. So you have the step T1 until T4, that will be your proof trace. And then you can see that the conclusion is the empty clause. So it proved like bottom. And then you can see that, okay, so the index, for example, of T1 was here, the clause that you derive is this one, and then you use a rule, which here is equipost 2. Here, the clause for T2 will be it will use the congruence for proving that PA equal PB, and he's using the premise A1. So this is why I was saying like stack and reference previous step. Okay, so A1 is your assume here, and then for proving this thing, you do a congruence, and then resolution. Like T3 and T4 that are used to conclude the proof. Okay, and usually the last step is always a resolution. Any questions so far about the format with a concrete syntax? No? Okay, perfect. So ality support this SFT lib logic, UF, LRA, LIA. Bit vector is still like a work in progress. So it's, I don't know how many operators of bit vector they cover so far. I think it's still not in the standard. Anya Barbosa is still working on this with one of his students. And also you have a quantifier free formula sublogic that you can attach to all of them, of course. The thing is, my work for now support UF, LIA, and I'm working on the reconstruction of the real and a little bit of the bit vector. So if I can finish that before the end of my PhD, that would be great. If you want other theory, like arrays, strings, this kind of things, then you need to look at something called Enoia, which is a new ality. It's based on SNT3. So if you have any question about SNT3, grad, because there is Pascal here, which is one of the main authors. So, and the thing is, you cannot implement this kind of logic and you're restricted to this thing. It's because like you need dependent type for like reasoning on string and array. Bit vector, they are doing a trick, but it's like, it would be suitable if you have like dependent type. It would be much more easier. So all the rules look like this. I'm just making categories for you to have an idea of what is inside ality. So you have some special rules, like okay, here is like the assume, which is like an admit. Whole is like if your proof trace you have a whole, then it means like this is a proof step that CVC5 cannot give you a concrete proof with a set of ality rules. So you have to call external solver to prove that. You can do subproof. There is some rule about resolution. Like you have resolution and TH resolution, but they are basically the same. It's just like one is just for marking that's the theory solver that do the resolution, and the other one is just the normal set solver. You have some tautological rule, like you have this one in the guiding proof, the equipost 2, which say that, so that's the equality that they use in the ality format. I keep that. And saying like, if you have not varphi1 and varphi2, and this, so it's a clause, but you can see this as a disjunction. So not this or not this and varphi2. Then you then if you see this, because you're in classical logic, so the negation of A or B give you A implies B. So you can see this as this thing implies this thing with this thing implies this thing. Okay. The thing is with tautological rule, some of them are just like very easy to manage, but there's some rules like this one where you have this famous triple dot, where you will need to do something because you don't know how many elements you have inside. So for the reconstruction, it's much more challenging. You have some rule for the linear arithmetic, and I put only the two main rules. In total, the format has like 96 rules, if I remember, or 98, something like that. And if you add the bit vector rules, then you have more than 100. So I just give you like, just here is for the categories of rules. You have some rule for dealing with quantifier and economization, and some rule about simplification. And I put here, like, I cannot give you the sequence, as you can see, for equisimplify, rule simplify, and LA and Lie generic, just because like there are more algorithms that you need to run. Like, so that would be like a challenge for the reconstruction to certify that the proof is correct. And then you have also other challenge with Aleph, which is like the ordering of the clause is not specified by the format. So sometimes there is some permutation that are going implicitly. Equality also, like you have some symmetry of the equality that is applied implicitly. Some proof step, I mean, more some rule or coarse grain. And so you need like more detail to reconstruct this thing. So you will need to analyze first the proof trace to do the reconstruction. And some steps sometimes are omitted. So one thing we are doing for helping us do the reconstruction is using Karka, which is a tool developed by Bruno and Daniel in the, I forgot the name of the university, I always forgot.
Minas Gerais.
Okay. So Karka is a tool that's like able to elaborate a proof, Aleph proof. So it takes a proof in input, it can check it for you, but it's just a ROS program that will check it. So it's not a proof assistant. So you might have a bug inside the checker, and the checker start to have a large code base also. But it's because it's written in Rust, it's with high performance. And it will elaborate you the proof, so it will remove a lot of implicit transformation and make you everything more explicit. But there's still things to be done for this. So for example, this is one of the things that the elaboration of Karka will do. That's our guiding example, and that's the proof that CVC5 found for this input problem. And you remember that during the resolution, it just told you that it's doing a, for example, for T3, it's just telling you that it's doing a resolution with T1, T2, and A0. And the thing is, when you look at this, and imagine that you don't have the orange part, then you don't know who is the pivot. And sometimes the order in the premise is not correct. So what Karka is doing for you is like you reorder things, like to give you the correct chain of resolution, and give you is also in arguments with the pivot, and then a Boolean flag to know if the negation is on the left or the right. Because I mean, like if here, like between T1 and T2, if the negation is on the negation of the pivot is on T1 or is on T2. And because it's at false, normally the negation should be in T1. Yeah. Yeah, of course.
So the ordering of clauses, it's in CVC, I assume.
Yeah. Yeah, no, in verity, it's that's right. Yeah, that's also a point I really wanted to go inside, because I didn't try to analyze really. I'm working mostly with CVC5. So there is also difference between SMT solver because they just output a proof of Aleph. There is a format, but they have different way to output the proof. Like Verity use more rules than CVC5, and also in the implicit transformation, they don't have the same. So as Pascal say, like the ordering of clause is not a problem in Verity, but it's a problem in CVC5. So that's an example of Karkara. And now, so we have like the CVC proof that we can elaborate, and we want to reconstruct them in a proof assistant in an automated way. So the decision is to use Lambdapi, because Lambdapi is like a hub or assembly language for proof assistant will allow, and if we do that, so if we plug SMT and do a transformation of the SMT proof into Lambdapi, and then we have to gain on this thing. Like the first one is like we are able to check that the proof is correct, but Lambdapi also, because it's like a assembly language for proof assistant, you're able to export your proof to other system. So the cool thing that we'll gain for this is like take a proof of SMT, transform it into Lambdapi, and then you can export it to Rock. Oh, I need to update this thing. Rock or Lean or anything that's like a double arrow. Lean is on a work in progress. Coq is the export to Coq is more mature for now, or even to Home normally. So that would be very great, like to have this thing and like sharing proof. So it's a little bit like having the reconstruction for free if you're developing a new hammer, for example. Hammer is something used in proof assistant, like an automatic tactic that will try to proof search and then like encode the problem into SMT. And the thing is, you have to go back to your proof assistant by creating a proof term. And then with this work, you get the reconstruction for free. So the pipeline look like this. The idea is like we take CVC5, we take Karkara, we leverage the checker and the elaboration, and we add a plugin inside Karkara that is allowing us to translate a proof. We take the AST of the Aleph proof and we transform it into Lambdapi proof. And of course, we add in Lambdapi our encoding of the Aleph logic and SMT logic. So I guess not a lot of people are familiar with Lambdapi, so I will just give you an introduction on this thing, a short introduction. So the Lambdapi proof assistant is based on Edinburgh logical framework. So that's the syntax. The only things that you have different from Edinburgh from LF is like you have rewriting rule. So it's like take a term or a type. If T match, then you rewrite the term to V. And so the thing is with rewriting rules, you need to prove that they are confluent and you preserve typings. Otherwise, you break subject reduction. Confluence is not guaranteed by Lambdapi, so you need, after you have write all your rewrite rules, you need to prove that they are confluent. Okay, you can do this just on papers or use some tools. It also support the higher order rewriting that I don't use in my work because like SMT2 is first order logic, but I guess for SMT3 that would be maybe interesting to have high order rewriting. The thing is with Lambdapi, its weakness is like there's no like what I call meta programming, like there's no type class or record structure. It's not very rich because as I say, it's like the assembly language for proof assistant. So don't expect to have all the nice feature that you have in your proof assistant like Rock or Isabel inside Lambdapi. And the set of tactics that you have in Lambdapi are very basic. We just started to have some automatic reasoning for the tactic, but I mean like being able to do programmable tactic. like what I'm thinking is like LTAC in rock. I don't know for Isabel, I forgot. And in lean is like metaprogramming in lean. So that's like challenging to reconstruct the proof of Aleph because of that. And the typing system of Lambdapi is exactly the same as the Aleph. So you have dependent type, you have basically it's just the P, you have a P type, and the only difference that you have with the Edinburgh logical framework is here, like the conversion rule. So usually in type theory, when two terms of P type are convertible, they are convertible at beta reduction. But now, because you have rewriting rules, they are convertible as beta and the rewriting rules defined by the user, which is like opening the gate to all the primordial angel or the primordial demon, like depending on you. So my encoding, like briefly, of the SNT logic in Lambdapi will look like this. It's something you find a lot in the literature in Lambdapi. So we have two universes of type. We have set for things that compute, prop for the proposition, and is where we will encode the booleans of SNT. For people that are familiar with Isabel, it's like should be fine. That's like technical stuff is like what we call a decoding function. So you take an element of set and then you give it a type. It looks like the decoding function of Gödel's. We have this one that's like for creating impredicativity. We have equality only on set, like what we call like small universe. And because of O, you can have also equality on proposition. And then the type of a clause is represented as like this. So it's a clause that looks like a little bit less. So you have an empty clause that is represented by this square. And I'm using this disjunction with a dot because the previous IT format was using this symbol instead of the comma. So you take a prop and then the rest is a clause. So it's like a list of proposition. And then a proof would be like a proof of a clause and it return you a type. And that's the symbol I use for concatenating clause that you will see during the resolution, because doing a resolution is like taking two clause, remove the pivot, and then like do the concatenation of the two clause. I simplify things a little bit, like in the code is not really like this, but it's just helping me for presenting you. If you want really all the details, like we can talk about this, of course. So after you like also do the encoding, for example, of the quantifier and the operators. So it look like this for the people that never see like Lambdapi. So for example, the bottom and the top are constant of type prop. Conjunction, disjunction, implication are like this. And then like this is a kind of first rewrite route that you have. Like for example, a proof of the term A implies B, you can rewrite it as a proof of A with the meta arrows proof of B. Negation is like a definition. And then I mostly put this thing here because like I want to say that we are doing a shallow embeddings and not a deep embeddings. So when you have like a quantifier fall or exist, then you just rewrite it to the P type. Okay. And of course we, so SNT is doing like classical reasoning. So we had these two classical axiom because our foundation is like intuitionistic. And we just add these two classical axiom to be able to reason with classical logic, which is the excluding middle here. And prop EQ, there's like from the if and only if, then I can derive equality. Because for SNT solver, like if and only if and equality is the same. Equivalence and equality are the same. So now that's for the operators and the logic. No, but now you have to take all the roof and give an equivalent in Lambdapi. So this is like basic rules. So for example, sometimes you can do it directly, like for these two rules. So for equi+2, that is like a tautology. Remember that it's like, so your context, we don't really care, like here it can be empty. So if you have a negation of A equal B and then not A and or not A and or B, then you can create a constant in Lambdapi. That would be like a proof of this clause. And we prove all the other rules that they are correct. And for example, also for resolution, then you can have this lemma. There's like, so the resolution will take like many premise, a list of premise that you have here. And then the conclusion of your step will be like all the clause with all the pivot that we can remove, which is like formalizing this lemma, which this is like just a binary resolution. So in the Carcara code, what we will do is like doing outputting a proof, printing the chain resolution by hand. Okay. We don't have like something like automatic in Lambdapi for doing the chain resolution ourselves. So the binary resolution will take two clause, the index of the element, two invariant to be sure that the index is in the size of the list, something to say that the element at I is equal to the negation at the position G of the other clause. So for PSI, need to be equal to the negation of QSG. And then the proof that you obtain is just like you remove the two pivot and then do the concatenation of the list by this symbol that I introduced you. Okay. So that's possible for some IF rule, but for other rules that we will see later, I will give you a focus on, for example, the arithmetic rule. You can see that you cannot write something like just a direct lemma. You will need to write a proof script. Because they are more algorithm than just like a lemma. Yeah.
So do we make this workshop interactive or do we?
I think so. Yeah, sure. It's just interact me whenever you want.
So the thing is, I mean, you can translate proofs of Alete. I mean, at least the easiest one into deductive, right?
Yeah.
But in deductive, I presume there is already some formalization of propositional logic, at least, right?
Not really.
Well, I mean, there must be some other people have done that for SAT.
You mean in deductive, like there is some other, like a standard library?
No, I'm not talking about deductive, well, naked deductive. I'm talking about some other people have done that for SAT. No. Well, they must.
No, there's not like I mean, if I understand correctly, you are speaking about the ecosystem of Lambdapi libraries.
Well, yes, I mean the whole stuff.
Yeah, that's a big weakness of Lambdapi. Like there's no already a standard library. I'm contributing a lot to add many things, but I'm the first PhD student that work on the reconstruction of let's say like an automatic prover, in some sense. And something like that look like that's something that do SAT solving. So no, there was like the lemma, for example, of resolution. No, it was not here. Okay. Like there is nothing about arithmetic for reconstructing arithmetic. It's kind of poor stuff. I mean, the ecosystem is kind of poor, so I have to redevelop a lot of things. And I think, for example, if you do reconstruction in mean, then you can profit about the fact that bit vector is already here, all the reals. This is why I'm not supporting the reals right now, because the reals don't exist in the standard library, and I have to construct the reals first and then do it. But if I started in rock or lean, then yes, the standard library will already give me it.
The danger is to have many definition of the Booleans, for instance, right? Everybody would start by, okay, this is what I call Boolean.
Yeah, sure. So we are creating a standard library, But as you can see, if you look at the previous thesis in Lambdapi, I think me and Melanie are the first one that will use the standard library. And now I think all the PhD students now are using the standard library that we are creating, but all the previous students, like the reconstruction of rock, was based on their own standard library, so they all redevelop again and again the same things. So we are trying to harmonize everything, and then we will realign everything. But yeah, that was like, I mean, for me, that was really time consuming to re-implement the bit vectors and reals, for example. It's fine because like there's already like many implementation of the reals, but because we have Lambdapi with user writing rules, you try to make like an implementation that take profit of this thing. So, and this is why I want to what I want to show in for the linear arithmetic construction. We have one way to do it that like take profit of Lambdapi features, and this is not something you can do with other proof assistants. So
the other danger is that you develop a series that suits your need, and you cannot reconcile it.
Yeah, true. Okay. Welcome to HP Wolf. Okay, so the translation of our tool looks like this. So the plugin that we add into Kakara, you output you something that look like this. So we create, that's the concrete syntax of Lambdapi. So all the symbol, the declaration of sort and declaration of function, you can see it here. So in Lambdapi, we use this term symbol for declaring a constant. So you have a type U that belongs to the set. Then this O will represent the proposition, as I said. So that's you represent the predicate here. Then the A0, A1, A2 is like your assert here. You can see that there is no proof term behind. This is because it's admit, they are like axioms. I have to do the term sharing by myself. So because like SMT solver also doing term sharing for avoiding like that the memory explode. So I have to implement also some term sharing on my side for Lambdapi. Because the problem with SMT pool is like the terms are quite large, like very large. So I have to do many things like what I call proof engineering, like doing sharing of terms, this kind of things. And it's not something you think so much when you're doing like a usual application of proof assistant, like you want to prove a theorem in math that is correct, you don't think about this kind of things. But because like here we are doing the reconstruction of SMT proof, which are very much more different than what the humans write, or I don't know if you use classification for proving that your theorem are correct, but I don't think you do that. And so to remind you the rest of the proof, so it looked like this. So the theorem and the three-step, two resolution, a congruence, and the tautology equipoise 2. So what we will do is like we create a lemma for each of them. And then like, so the T0 will be like the direct application of equipoise 2. Here is the congruence that we have in the standard library, but read this as cong. And then resolution, the resolution, and the resolution. And here you can see that we have to output the chain resolution. So we construct the chain resolution in Rust. Okay, we don't have like a meta tactic that will like create the chain resolution. I understand it's quite hard to read. Like it's generated, so don't expect this to be so clear. Okay. So for something more harder than just like reconstructing something in like the guiding example, for example, I want to talk about the arithmetic proof. So I'll take another guiding example. And so I don't go again, like you have some assert and then you want to prove that things, some assume, some step, but what is interesting is this one, I like generic, which apply the Farkas lemma. So it's telling you that, okay, this three clause, this clause with this three literal, will be like, will give you a contradiction. And the coefficient that you have to use for the Farkas lemma is this one, okay? But it's not telling you so much things. And for arithmetic, this is a set of rules that you have in LF. So the two main rules, LA generic, LA generic, which is the same as LA, but just like limited to integers. Some tautology also. But and some like this one, the normalization of a polynomial and rules that do constant folding. And the thing is, for LA generic, I told you that some of them look like algorithm. That's the algorithm for LA generic. So you have to reconstruct this thing, and then of course you cannot just give a lemma and say, oh, it worked. You have to create a proof script for that. So that's the refactor one, because like there is some typo and some step that can be simplified or improved in the original Aleph one. So basically, trust me, the first step, the first step is just like, it's telling you that SMT solver want to work with only greater and greater than equal. So everything that is like lower than equal will be transforming into greater and greater than equal. So you do negation, this kind of stuff to like normalize all of this. So this is step from 1 to 3. Normally it's only normalization. So step 2 is just like pass everything that you have on the left side of your inequality to the right side of your inequality to the left side. So at the right side, you have only constant. Okay, this is why like you start with this thing, a bow tie that represents like any inequality symbol. So you have the left part and the right part. What you want is like take this thing, put it on the left, and then here you have only the constant. That's the step 3 will be applied only if you're in the you have only integers. The step 4 is like apply the coefficient. And as you saw, like some of the coefficient are they are always rational, but when you're sometimes you can cast them to integers, but just using the least common denominator. This step, for example, is not in the original Aleph. This is my version that added this thing. The step 5, again, do some like strengthening and this kind of thing. Apply the coefficient to all your inequalities that the solver give you. And finally sum the resulting literal is give you a trivial contradiction. And it's just telling you this, but not the details of the computation. So you see that this thing will be kind of hard to reconstruct with just like without like an algorithm or at least a proof script. So that's, for example, a challenge to reconstruct this kind of proof. That's an example, or it worked. Yeah. Yeah.
I'm confused by step 4. What is step 4 doing?
It's like if you have rational, you know, and then like you have, for example, I mean, here in the example, okay, I'll go on the example and then you see. Okay, so LA generic, like if you take this close, for example, like you have f is greater, not f is greater than 0, no, is lower or equal than 0. Then you have 1 plus 4f is lower or equal than 1, and it's telling you that the coefficient will be 1 and 1 on 4. And this thing, then you can cast it into integers with using just the least common denominator, and then you come back in integers. Because remember that the rational or not, it's a work in progress. So this is what I have to do. Strangely, like as people from SNT are quite surprised when I say like I have LA and not the reals yet, and they are saying like, but reals are more easier. No, because they are more complicated to do in the proof assistant. So it's like kind of inverse.
The CVC5 doesn't.
What? Flattening all the coefficient?
Having this, I think Verity doesn't have this kind of cases.
Yeah.
CVC5.
Yeah, I think so. Oh yeah, something I forgot to mention. Like when you are with step LIA generic, you don't have the coefficient. So there is some trick that is done in Kaka, but I don't want to go into this kind of details. But if you want to hear more about this, just tell me, we'll discuss this after. So the algorithm, like as I say, step 1, step 2, and step 3 are just like normalize your terms. So for example, here you have 2 lower than equal, so you want to transform it into greater than equal. Then this arguments here, you're using rationals, so you can clearly like cast them into integers by just using the LSCD. Apply your coefficient, then you have this final sum that so you have all this literals, and then you can like just sum all of them and then prove that you have something like 0 is greater than equal to 1, which normally I think additive format force you to have something like 0 is greater than equal to a constant or greater than a constant, but in application like CVC5 don't do that. Like you can have something different than 0 here. I'm not so sure. I think I had this case once only, so I don't know if it's a bug or I don't know. It's a word. It's just like
Your algorithm anyway, you put everything on one side.
Hmm?
In your algorithm, you put everything on one side.
Yeah, just like here, the added format forces you to have a 0 here.
Yeah, but the point is that how can you have something else than 0 because you have coefficient? I mean, you have the variables on the left, which mean that the only way to remove variables is to have 0.
Yeah, because you want to cancel all the variables.
Exactly. So you cannot have something else than 0.
You can have a plus constant.
Yeah, but they put the constant on the other side.
They put only the constant on the other side will be like the one that is like on the right hand side, this 2. So I don't know if you have still yeah, by normalization normally you should have only like yeah, I agree with you. No, I think maybe, but that happened once, so I really think like all the time, most of the time you have 0, just like it happened to me once.
Or maybe it's 1. I mean, the contradiction, you can always have the contradiction 0 greater or equal to 1, but maybe it's the one that you don't get always by the function.
So for doing the reconstruction of this kind of proof, we need to do some proof by reflection technique, which is like we will use the computation power of Lambdapi to like normalize the term, because as you see, like there is a final sum to do. And on the example, for example, when you have something like this here, you're lucky that your F and your F are next to each other, so you can cancel them. But imagine that you have a much more longer expression, and then like you have an F here and an F there with other variables in between. You will not be able to simplify your term easily. So you have definitely a problem of AC normalization. And for solving this problem, we are doing what we call a proof by reflection. So we'll take here I'm just like putting equality, but think about any inequality. So you're starting in Z. You have like an algebra that will represent the integers. So we have a function that will reify this thing into this algebra. In this algebra, you have a normalization function that will like normalize your term. And then you have a denotation function with the arrow that go on the downside, and it takes like your algebra and interpret this thing into integers. So it's like there's an isomorphism between Z and G. G is because like it's a group, or even a ring here. I don't support yet the division. And as I say, there is two ways to deal with this thing. So one way is just like pure Lambdapi. You use something called the modifier associative commutative. So the Lambdapi kernel is able to like normalize your term. With it, if you say that this symbol will be associative commutative, then you have like an internal normalization function. So the Lambdapi kernel will do that for you, and that will be quite fast, but you need to trust, of course, the Lambdapi kernel. The second solution, so this one I call it inner, this one I call it outer. Inner because it's inside the Lambdapi kernel, this one outer. This is my own terminology. I don't think you would see that in the literature. I create terminology. So the outer normalization is just like you do the normalization by your own, and then like you have to prove that your normalization is correct. But then you do like symbolic execution, so that might be quite slow. It would depend a lot of the implementation of your proof assistant. We support both. Like if someone is very skeptical about Lambdapi, then you can do the outer, and then you be sure that the proof is correct.
But how can you not trust the Lambdapi kernel?
I don't know. I think there's some people that are very skeptical. So
I mean,
I want to host everyone.
Yeah,
if you're
but-
very somewhat skeptical.
if you're using Lambdapi, you have to trust. You have to trust that it's.
Yeah,
not-
but that's the question, like how you prove that Lambdapi is correct, for example.
Yeah, or do you mean you can, or do you mean you can have a smaller kernel if you don't do inner normalization?
Yeah, the normalization is not quite big. It's just like, okay, there's for now, the normalization, if you use associative commutative, you will see this in the benchmark, but it can be very slow on big term. It's very fast. Like we are working in a new implementation with Frédéric. It's not released yet, but so the new implementation is very fast, but we are not sure it's correct yet. What we are doing. So see, I told you that you need the two. I'm not kidding.
It's easiest to be efficient. It's easier to be efficient if you're not sound.
Yeah, sure.
Yeah, but I'm trying to compare it to, let's say, Isabel, where you have the kernel, and if you just say, yeah, don't trust the kernel, and you just should stop using Isabel. That's the part where I don't get the argument.
Okay.
Because everything is going through the kernel, so if you don't trust the kernel, you just don't trust anything. So you wait.
Well,
wait
let's say like this one is like it's a feature in the kernel, the associative commutative, like it's very specific. Let's say like I don't know. It's like, let's say it's like it's in alpha version. This thing, like even if I use Rock for example, when some feature like user rewrite rules has been just introduced, and you have a big flag saying like it's on battle test. So let's say associative commutative is like on the flag like it's an alpha version. Like
Okay.
we're not so sure for now. So the idea is like to have your algebra that represent the integers. So you have the plus this plus, the O plus will represent the plus of the integers. This is the one that will be associative commutative. The variable that's like your integers, a coefficient, and that will belong to the algebra. Multiplication opposite or something like that you can ignore in some sense, because of the right rules that I will give you, and then the constant here, and that's on this part the reification, on the right part the denotation. So you go from the integers to your algebra, and on your algebra to the integers. So they are supposed to be isomorphic, and there is another modifier that we are using, which is sequential, where the magic happens, because normally, if you have done some proof reflection in Rock or Isabelle, you have always something that's like meta and you cannot reason about. And for Rock, at least you need to use some LTAC, where here with the power of Lambdapi, you don't need to do any meta programming because you have a sequential things. So that means like we can do the verification directly in Lambdapi, which is not something you can do with the other proof assistant. And this thing is just saying like, okay, normally this set of rules are not checked like linearly. It's just like you will do some pattern matching, and when you can apply a rule, you do it. What here we are saying by saying that this one is sequential is that you will try them in order of the definition, one by one. So if it's a 0, then create a constant. If you see a plus, then create the O plus, and then reify the two subterms, negation, like here the multiplication by the variable and the constant. And then in the case that you have a variable, this is what you do. You do that's your otherwise case, and then like it's just like, okay, this thing that you match, then just inject it directly inside the constructor var, and then just say it's 1 times your variable. Okay, there is a reason why we have to have a shape of put the coefficient inside the variable. I will explain you why. It has to deal with the order that Lambdapi use for doing the associative commutative. So that means like if you have done some proof by reflection, usually you have like a map that will say, okay, this term like correspond to these indices. Here, because of Lambdapi in the sequential, the magic is we can embed the term directly here, where you will see that in the outer method, like here, it will be a natural number with a map that will carry to say, okay, this thing is this thing. Here is like, we can just embed directly the term. So proof by reflection in Lambdapi are quite easy to do, and I feel like they are much more easier to do than the other proof assistant. That's my own impression. Lambdapi is great. Okay, so the order that is used inside the kernel is you have a total order on the G terms, and for example, if you have like 2 constant, then you just like compare like C1 and C2 variable, or because like they are like in the order they have a bigger weight than constant. And if you have 2 variable, then what you do is like first you compare X and Y, and then if they are equal, you don't move that, and if Y is equal lower than X, then you would permute. So this is something that you have, like for example, in the example, like I have a variable C1X, a constant, a variable C2, again a constant, C3, C4, and then like I'm assuming just a lexicographic order, and I want like for example like X, all the X put next to each other and all the Y put next to each other. And this is what Lambdapi will do for you. So it will like, after you normalize this thing in the kernel, like the 2 constants will be put next to each other on the left side. And then you have the X next to each other, Y next to each other. So you can like simplify everything directly. And that's after the rules that we have for the simplification of the term. Just look at the red one because they are the most important. As you see, like if you have a constant 0, you can just like rewrite, so 0 plus X, you can just rewrite to X, for example. But the main one of this thing, like if you have 2 variable X and X, so that's a nonlinear right rules because like you have 2 times the same element on the left side. Then you say like, okay, but then fold this thing into C1 plus C2. When you're in the associative case, then just like unfold this thing and then do the C1 plus C2 for X and continue with the Y, and then for constant, same. Okay, so this is how we fold it after they have been normalized by Lambdapi. So Lambdapi do first a step of normalization, then he apply one of his rule, then we do a normalization until we arrive to a term that cannot be reduced anymore. So the proof, like as I said, like sometimes you need a proof script, and this is like a proof script that we generate. So all the step from the line 2 to the line 13 is about like the step 1 to 4, about like just like changing things, normalizing the inequalities, and using only greater than equal or greater than. And finally here the reification, like you reify your left part and your right part. And because of the normalization is done in the kernel, okay, so your normalization function don't appear here because it's just the identity function. Like, so then like he will do this thing by, he will reduce the term by itself. So, and then you can prove that it brings to a contradiction, and then prove that you have a contradiction, that's all. The other way that we are doing it is just like the normalization, so the outer version, like the normalization is now concrete. And then like you have this famous list that will be your environment that will tell you all the interpreted symbol will be put into this list. So your denotation function now will use this map between the interpreted symbol, like the variables, and that's all. So you will verify, and then you have a real normalization function that you have to prove that it is correct, and also then the denotation function, but you just follow the same pattern that I show you for the inner version. Exactly the same. Just normalization now is like explicit. And to give like some what is doing the normalization, we just re-implement what Lambdapi is doing. So now your algebra will be just the group type in a more shrinking way. Like the variable, now you have an index to tell you what is the element of your is uninterpreted, and you put the your integers inside this context. So that's like a pointer. That's the coefficient, constant, and multiplication. And we'll reify into a list of groups. And then the normalization function is the same. So I have a merge sort for the list of your group that will put like your variable that are the same next to each other. And then like add the coefficient when you can. And the function that do the remove 0, which means like you would just go on the list, and all the variable that have the coefficient at 0, you will just remove them from the list. And then we have a theorem to prove that the normalization is correct. Okay, so if the evaluation between the two methods is like a little bit what I told you, like one is like you need to trust the Lambdapi kernel for the inner version. The other approach is slower because it's doing like symbolic execution. Okay, so we have some problem for big example. Yeah.
Where did the big example come from?
I'll do everything on SNT-lib. I'm going on this thing. So for the evaluation, and then if I have time, I will speak about a practical application of my work, for example.
We won't have time.
But
You have 2 minutes.
I have 2 minutes. Okay, so that's okay. It's fine. It's fine because what I have left is not so big. So don't worry. So the logic is so everything comes from the SMT-lib SMT-comp, SMT-lib benchmark, SMT-lib benchmark. So I have benchmark from LIA, QF LIA, UF, QF, and some things. That's my application case about TLA plus, because I want to reconstruct proof from TLA plus. And okay, basically it worked pretty well for sledgehammer, all these kind of things. It's easy to increase the number of proofs that is accepted. It's just because sometimes you don't support one of the rules, so the proof fail. Okay, so add just a new lemma, and then you have like thousands of proofs that finally pass. The one that's the most interesting that shows the weakness of the reconstruction with AC is rings. So it's in QFLEA. You have rings, which has 294 samples, and we are able to check only 7. But CVC5 is only able to output like, I think 80 proof of them. So it's already a challenge for the SMT solver. Karkara is not able to also check all of them. And now after the reconstruction is even more harder. Like, it's just like the term was so huge, like gigantic. That's like a very challenge to reconstruct rings.
Would you say that the size of the proof that you need to reconstruct is the main challenge? So it's really the
Can be
scalability?
like, this is what I say, like it's like proof engineering at some point.
So the other, for example, ultimate in the LIA, where there's also a large gap, it's the same kind of problem? Or?
They come from model checking, so.
I forgot why ultimate. I think ultimate is because of the elaboration. That's the problem. CAV is because I don't support one of the rules, so it fell. Same for Sledgehammer, if I remember. But yeah, Tokener worked well, and Tokener is an industrial one. I'm able to reconstruct most of the things. So if the people of Tokener has some job position, I'm open. Okay, that's for the benchmark. And my application case, if I go quickly on this thing, is just like, TLI Plus is a proof assistant that we are using in the Veritas team. And is using SMT solver mostly for its reasoning. So if we are, and for now, it's don't check that the result of the SMT solver are correct. So there is no proof term or tactics. It's just like encode the problem into SMT and then like check that the SMT is saying unsat. And if it is, then you say, okay, I can continue in the proof. So one thing to verify the proof of TLI plus will be to like encode, verify that the SMT is correct. And then like if we do that, then we solve the problem of TLI plus. So okay, basically TLI plus is allowing you to do like a specification of some distributed system or a reactive system. You have this language, this nice language is used temporal logic and higher order logic also. Second order, so that's a proof in Cantor. I will go fast because I don't have time anymore. So each step will give you a proof obligation. That's the Cantor theorem of non-bijection. And then that's the famous diagonal argument of Cantor. That will give you like many proof obligation. And then we just like take the proof trace that CVC5 found and then check that this thing is correct. So that our pipeline is TLIPS like call SMT, but now we'll get the proof, we'll add get proof, we'll like add a call to Karkara, and then like we verify this thing into Lambdapi. And yeah, I didn't mention that before, but okay, for the LI generic, Karkara is doing something that is calling back again CVC5 to try to remove the LI generic, because in LIA generic, sorry, you don't have a coefficient. So it's trying to find another proof where you can have a coefficient.
Why don't you use the verity for that? Because you don't have the coefficient.
Karkara can call anything that's like accept then output Aleph. So yeah, we can like that.
But you could reuse verity to get the coefficient just for the LA generic stuff.
Okay.
But you wouldn't have to.
Okay. Okay. Yeah. Okay. So the further work I'm working for now is like finishing the support for big vector and reals. And I'm also working on another type of rock export with the new feature of user-defined rewrite rules, so that the export of Lambdapi would be like kind of exactly almost identical to what you have in log. Thanks.
Question. I have time for one quick question for the coffee break. Okay, can you go to the SMT benchmarks? How do you do you have in the last row you had NIA benchmarks and
Oh no, this is just
it's just a okay.
this is just because like
the header is NIA. And
yeah, there is NIA, but I'm pretty sure you can remove this thing. Like I forgot to mention that.
Okay.
Alright. But there is nothing about like none. It's just like in TLI plus you can write polynomials.
Just produce NIA.
So we have to write. Yeah, but you can name it.
Then I would suggest that for more questions, we can just hijack the info at the coffee break.
Don't forget to subscribe and see you next time.